Okay, let's get started, please. There's space in the front if anybody wants to move a little closer. Okay, so first let me say that I'm sorry I haven't finished grading the exams, but I should have them done in the next day or so. If people want to write to me and say, I can probably like scan them and send them to if you're anxious to have them before spring break, or if you prefer to leave them until after spring break. Yes, Josh.
Can we pick them up if we stop by during your office hours
tomorrow? So I'm not sure I'll have them done by tomorrow, to be honest. It's more likely they'll be done by Friday.
By Friday.
Yeah. If you want to pick them up on Friday, that's fine. Yeah. Okay. So today we're going to go backwards to chapter 3, numerical sequences and series. Okay. So there's not that many definitions. Okay. So chapter 3, numerical sequences and series. Okay, soon we will, after this chapter, we will jump to chapter 7, which is sequences and series of functions. Okay, so right now we're going to do kind of a simpler version of that, numerical sequences. Okay, so so first off, let's start off with the main definition. So suppose you have a function from the natural numbers into x, right? So x is a metric space. Okay, so this is a sequence, right? So it associates with every number a point in x, right? So with every number you associate some point p of n. Okay, right? Usually when you're talking about sequences, as you probably know already, we don't write p of n, but rather we write p sub n. Okay, we write p sub n, right, for a sequence. And sometimes instead of writing it like this, then we'll just abbreviate the whole thing as just as this p sub n from n equals 1 to infinity or whatever. Okay, so you start off with some sequence. And we're going to talk about what it means to converge, right? So if there exists a point in x with the property that for all epsilon greater than 0, there exists some point n in the natural numbers such that the distance from Pn to P is smaller than epsilon for all n greater than n, then we say Pn converges to P in x. Okay. So the picture you want to keep in your mind, the image you want to have in your mind is like, so here's your space x, right? Here's your vector space x, and then here's the point P. And what we're saying is that there's sort of a clock, right? There's sort of a clock that goes on associated with your sequence, right? Time 1, time 2, time 3, time 4, et cetera, right? So for Pn to converge to P means that, right, given any neighborhood, right? So given any epsilon neighborhood of P, right? Given any epsilon neighborhood of P, there is a time past which all elements of your sequence lie in that neighborhood. Okay, So you can make them as close to p as you desire, right? That's what it means for the limit to be p. It means that, if somebody says, I want you to stay within, an inch, I want all your values to stay within an inch of p, there's a time past which everybody is within that inch of p. Okay, so this is the sort of what you want to keep in your brain. Right, this is the formal definition, but what it really means is you want to think of it sort of visually like this. Okay. Okay. So right, so this converges to p and x, as I've written over there. We also write this as pn goes to p. We also write the limit of p sub n as n goes to infinity equals p. Right, those are all the same things. Okay. Okay. And if no such p exists, right? If there's no point with this property, then we say that the sequence diverges. Okay. Notice that this depends on x. Convergence depends on x, depends on the metric space. Right? Depends on the metric space, because the point has to lie in the metric space. Okay, this is important. So for example, if I look at the sequence 1 over n in 0, infinity, then that diverges. Okay, we say that diverges, right? Because there's no point in 0, infinity that it converges to. Okay, so this sequence diverges in 0, infinity, but if we were in closed 0, infinity, then it would say it converges, right? With the usual metrics. Okay, so convergence depends on x in two ways. One, it's got to have a point that you converge to, and two, of course, you have to converge with respect to the metric, right? If you change the metric, then maybe it doesn't converge anymore. Okay, everybody all right? Yeah.
Is it possible for a sequence to converge to different points in different metrics?
Yeah, I think that should be possible. I don't have any good example of that. One kind of funny example is this so-called p-adic metric that's used in number theory. So this is a metric that you can put on the rational numbers, and then the closure. If you try to close the rational numbers with respect to this metric, you get an entirely different metric space. So you get you don't get R, you get something else. So things that converge with respect to the standard Euclidean metric almost definitely aren't going to converge with respect to the p-adic metric, and vice versa. So you can look that up. But I don't have any good example for you regarding your question. Any other questions? Okay, so we're just doing, we're just talking about convergence of sequences. You've probably seen this before, although not in metric spaces. Okay, so let me put up a few implications of convergence. So theorem about implications of convergence. Okay, so again, we're going to start off with Pn sequence, right? A sequence in the metric space X. Right? Okay. So here they are. First off, Pn converges to P, some point in X, if and only if, for all neighborhoods, for all radii, the neighborhood of, every neighborhood of P contains almost all of the P sub n. And when I say almost all, I mean all but finitely many. All but finitely many of the P sub n. Okay. Second, something that we've seen something similar to this before. If P sub n converges to something, and P sub n also converges to some other point, then those points must be identical, right? Then P and P prime must be the same thing, right? There can be only one limit. Okay. Number 3, if P sub n converges, then the sequence must be bounded. Right? That is, it must lie in some finite neighborhood. Number 4, so if you have a subset of X and a limit point of that subset, then there exists a sequence P sub n if E such that P sub n converges to that limit point. Oh, yeah, Keisha.
Yeah, for the first point,
Yeah.
you say all the finitely
Mhm.
require the neighborhood of P.
Yeah.
Is that the same as saying the complement of the neighborhood of P is finite, or is that different?
The complement of the neighborhood of the P.
Or it has finite neighborhood points.
Yes, that's the same thing. Yeah. So the complement of the neighborhood would contain finitely many of the P sub n. Yes, that's the same thing. Yeah. Other questions? Okay, this last one is sort of a relation between the notion of limit points that we had earlier. Jacinta.
I just have a question. Did 2 and 4 imply that there's only one limit point?
Sorry.
Did 2 and 4 imply that there's only one limit point for a sequence that converges?
So that's what two is saying, right? That there's only one. You can only have that one. There's only one limit for this sequence. Yeah. Oh, I see what you mean. Yes. So you were talking about limit points.
Yeah.
Yeah, limit points. So you're saying, suppose you have a sequence. Could it have more than one limit point?
Yeah.
Right? And you see that that's impossible, right? Because if it converges, right? If it converges, then you know that there's some point, and only every neighborhood is going to contain all but finitely many of the elements, right? So if you have some other point, it couldn't be a limit point, right? Because in order to be a limit point, remember, every neighborhood of yours will have infinitely many of the elements of the sequence, right? So that's impossible. Yeah. Yeah. So what this is saying here is that if you are a limit point, then you can find a sequence whose limit is u. Okay, right? Any limit point of E, there's going to be some sequence in E that converges to that point. Okay. But it's, the opposite isn't true. If you have some sequence that converges to a point, that doesn't mean that it's a limit point of the sequence. For example, you could have a sequence like this where every element is the same, right? Where every element is the number 1, right? Well, the limit is 1, but that's not a limit point of anything, right? It's just a solitary point there. Okay. Okay. So let's do these. Okay. So let's do this. Let's prove the first one. So this one says that if you converge to x, then for every epsilon, your epsilon neighborhood is going to contain almost all of the piece of n. Okay, so let's go forward first. Okay. So suppose that Pn converges to P and fix a radius, fix a radius. Okay, here's P and here's the radius. How do I know that that neighborhood contains all but finitely many of the piece of n? Kishan.
So in the definition, we have that n greater than some n,
Yeah.
or n less than some, and or there's n points outside of the contour.
Very good, very good. So just by this is just by the definition, right? You say, well, look, by the definition of convergence, we know that there's some time such that if you're past that time, then all of the piece of n, right? Then piece of n lies in this epsilon neighborhood, right? So how many guys could be outside, right? So that tells you that there are at most n elements outside of that neighborhood, right? So that's just the definition. Okay, right? Is that okay? Everyone all right with that? Pretty straightforward, right? We want to show that there's only finitely many guys outside. Well, we know that this is some time past which everybody's inside. So the only guys who are outside are those finitely many points before that time. Okay, so I hope that's clear. Okay, now going back the other way. Suppose we know that we have this property that every neighborhood, right? Every neighborhood contains all but finitely many of the piece of n. And we want to show convergence, right? We want to show that it converges to P. So suppose we have this property. We want to show that given every epsilon, given an epsilon greater than 0, that there exists a time, right, such that if you're past that time, then Pn lies inside of the epsilon neighborhood P. Okay. How do we show that such a time exists? How do we show that such a time exists? We know that there's only finitely many guys outside, right? So by assumption, there are only some like Pn1, Pn2 to Pnk that lie outside the epsilon neighborhood, right? So what time do I choose to ensure that everybody everybody past that time lies inside the epsilon neighborhood. How do I construct my time? Anybody see it? Just in it. Just take the maximum, right? So let n be the max of all these indices, right? Let n be the max of all these indices. Then certainly if we're past that point, if we're past that time, we're not going to be one of these guys, right? Right? Then if n exceeds n, then we're guaranteed that p sub n lies inside the neighborhood because it's not one of these guys. Right? The only guys who were inside were these guys, number 1, number 20, and number 7. Right? So if you choose the maximum as 20, choose your capital N to be 20, then certainly 21 is going to lie inside because it's not 1, 7, or 20. Right? Okay? Right? Because since n is bigger than any of the ni for I equals 1, okay. Right. It's not one of the bad guys. Okay. Okay. Okay, everybody all right with that? Anybody have questions about that? Yeah, Eric.
It feels like only capital N is important. So if we have a sequence already that's convergent, can we add anything else to it and it will still be a convergent sequence?
Yeah, so you can add, if you add some finite junk at the beginning, it'll still converge. Right? As long as you add a finite amount of you can add all sorts of nonsense at the beginning, as long as it's finite, it's not going to affect the convergence. Yeah. Good. Any other question? Okay. Let's see. Which one do you want to work on? I have leave these as an exercise to students. Which one is appealing to you? This one? So do you want to show that the limits are equal, that the limits are unique, that the sequence, a convergent sequence must be bounded, or this thing about limit points? Let's vote. Who wants to do number 2? Who wants to do number 3? Number 4. Okay, number 4 it is. Okay, everybody work on number 4 for 3 minutes or so. Well, I'm having you guys work on number 4 as an exercise. Okay, turn to somebody nearby and talk with them. Eric, you have nobody.
You just need a piece of energy in that epsilon. The thing is, you won't necessarily exclude the first one. Think about if E was.
Maybe we can do like this distance between and that first point. So take that as R and then do R over 2. That's very easy. Yeah.
But do you know there's a factor of X here around the limit? Or you can with something left. You. Yeah, there's something trying to see that. Yes. Yeah. Take a point, take its distance, take half the distance. Yeah, that works.
Okay, does anybody want to say how they come up with the sequence, right? So you have P, the limit point of E, and you want to show that there is a sequence that converges to that P. How do you come up with that? How do you construct that sequence? Anybody? No? Yes, Eric, yes.
Would it be okay if we say like it's a limit point? So we take an arbitrary epsilon neighborhood of radius epsilon, and we pick a point in that neighborhood.
Okay.
So that would be our first point,
Okay.
P1. And then for our second point, we create another radius. That's the distance. That's half of the distance between P and P1.
Okay.
And then for that one, since it's a limit point, we are guaranteed to have something E in that radius as well. And then that's our P2. And let's keep doing this. We can do this forever. And
Sure. Okay, great. So you're saying, well, look, let's fix an epsilon. You could say fix epsilon equal 1 or something like that. It doesn't matter. You could fix an epsilon greater than 0. Okay. And then you're saying, we know since P is a limit point, right? Since P is a limit point, we know there exists a P1, an element of E, such that P1 lies inside of that epsilon neighborhood of P, and it's not P itself. Right? Okay. So then you get this, right? So you fixed your epsilon, you know that there's some P, you fix your epsilon, you know that there's some P1 inside there, right? And then you say, well, the next thing we're going to do is say, let epsilon 2 be half of the distance from P to P1, right? So you go like this, and you say, let epsilon 2 be half of that distance there. Okay. Then we know that similarly there exists a P2 that's in E, and it's also in the function epsilon 2 neighborhood of P, right? And then you just keep on going in this way, right? And you're ensured a sequence where the distances, right? The distances of from P to Pn is always like less than 1 over 2 to the n minus 1 times epsilon, right? That's what you're ensuring by taking half of the distance every time. The first distance was epsilon. The second distance, right? The distance to P2 is smaller than half epsilon. The third distance is smaller than a quarter epsilon, and so on and so forth. Right. And so you see that these Pn conversion. Right, because if somebody gives you an epsilon, then you simply need to choose n big enough that this thing is smaller than epsilon. Okay. So that's good. That's good. Okay. So the only thing that I would say is that you actually don't have to worry about them being different points. It looks like you're trying to ensure that P1 and P2 are not the same points, but actually it doesn't matter. They could be the same points, right? All you need to do is ensure that the sequence converges to P, right? So you actually didn't need to do this thing here. You just needed to take epsilon 2 to be half epsilon. Okay. So yeah. So if I were to, this is completely fine, but it would have been fine to just take your epsilon n to be, say, 1 over n. Take your epsilon n to be 1 over n, and then you know that there's going to be points within distance 1 over n to p, and then use that sequence. Okay. So that's fine. Okay. Okay. Any questions about that? Okay. Let's go on. Okay. So, as usual, we'll have some theorem about limits and arithmetic. So, convergence and arithmetic. So, say that you have two sequences, Sn that converges to S, and T sub n that converges to T in the complex numbers. So you've got sequences of complex numbers. Then, as you expect, the limit of a sum equals the sum of the limits. Right? The limit of some scalar times the sequence equals the scalar times the limit of the sequence. The limit of the product equals the product of the limits, and the limit of the quotient equals the quotient of the limits, as long as you don't divide by 0. Limit of the quotient, sorry. The limit of 1 over s, the limit of the reciprocal equals the reciprocal of the limit, which gives you the quotient statement, as long as the SNs are all non-zero and S is non-zero. Yeah, as long as this makes sense. Okay, so these sorts of statements are maybe not the most exciting, but it's a good practice for you to see how it's done. Okay, so it's just basically practice on how to give limit arguments. Okay, so I'm not going to do the first two because those are I'll let you read those. I'm going to do the third and the fourth because those are the more interesting ones. Okay. Okay. So proof of 3. Okay. So we want to show that the limit of the product is the product of the limits, right? We want to show that the limit of the product is the product of the limits, or if I rearrange it slightly, that this limit is 0, right? That the limit of the product minus st is 0. Okay. And you're given that Sn converges to S and Tn converges to T. Okay. Okay. So observe, make the following observation, that we can rewrite this Sntn minus St in the following way, as Sn minus S, Tn minus T, plus S, Tn minus T, plus T, Sn minus S. Okay, so we take the thing that we're trying to control, and we rewrite it in this kind of funny way. Okay. Why do we do that? Because we're trying to introduce things that we have control over. Right? This is the thing. Right? We have control over the distance of Sn to S. We have control over the distance of Tn to T. Right? We don't have those things here. They're not evidently here. But if we write it in this, if we rewrite it in this clever way, then they are here. Okay? Okay, so we try to slide in what we have into the thing that we're trying to control. To slide in the things that we have control over into the thing that we're trying to control. Okay, this is kind of a general philosophy and analysis. Okay. Okay, now this is good, right? Why is this good? Because what do we have here? This is the this is a constant times something that goes to 0, right? And so we can use this second property to evaluate that, right? That's just going to be S times the limit as n goes to infinity of Tn minus T, which is 0. Okay. Similarly, we can use 2 on this, and we can use 2 on this as well. Right? So we use 2 on both of these. And in fact, we're using 1 because what we're saying is that we can, that the limit can be broken up into sums of limits, right? I can take these limits independently, right? To evaluate this, right? To evaluate this limit, I can take the limit of this plus the limit of this plus the limit of this. So, tacitly, I'm using 1 as well. Okay. So what does this do for you? It says that we don't have to worry about these things. We're trying to show that this limit is 0. We know that these guys go to 0, so it suffices to show that the limit of this thing, this product, equals 0 as n goes to infinity. Okay. So this is that business of sort of factoring out the information you have, right? So we know that Sn converges to S and Tn converges to T. That basically shuts down the problem. That basically wipes out half of the problem, reducing our problem to a smaller problem. Okay. Okay. So suffices to show that this goes to 0. So let's do it, right? So given an epsilon greater than 0, we want to show that there's some n past which this thing is smaller than epsilon, right? So choose n1 such that Sn minus S is smaller than root epsilon for n bigger than n1. Right? So we know Sn converges to S. So sorry, that should be over here. We know Sn converges to S, so we can choose an n1 such that this happens. Right? Okay. We can choose an n1 such that Sn is within root epsilon of S, and similarly can choose n2 such that Tn minus T is smaller than root epsilon for all n bigger than n2. Right? So that's just by because we know the convergence of Sn to S and Tn to T. Okay. So then, what's our n going to be? The bigger one, right? So let n be the max of n1 and n2. If n is bigger than capital N, then both of these things are true, and so Sn minus S times Tn minus T is smaller than epsilon as designed. Everyone getting how these arguments, how this argument works? Any questions? Right. We're trying to show this limit equals 0. We pull this trick on it. We rewrite it in a clever way so that we can use the fact that Tn converges to T and Sn converges to S to wipe out half of the problem. And then we say, okay, well, we need to make this thing small. Well, we know that we can make individually each of these things smaller than, we need the product to be smaller than epsilon. We know that individually we can make each of these things smaller than the root of epsilon. And that'll do it. Okay, let me do the last one. Is it okay if I erase this? Anyone still copying? Okay, I'm gonna erase this. Okay, so the last one is, okay, so proof of 4. We want to show that the limit of 1 over Sn is 1 over S. In other words, the 1 over Sn minus 1 over S equals 0. Right? Sn goes to infinity. Right? And again, we make a not so clever, this time we make a less clever observation that this 1 over Sn minus 1 over S is, of course, the same thing as S minus Sn over Sns. Okay, and you see why that's good, because we know that S minus Sn is the thing we have control over, right? And we can control it. We can make this as small as we want. Okay. And then this thing on the bottom, what do we know about this? SNS. We know we can make Sn close to S, right? We can make this close to S squared, right? Okay. So let's think about this. Suppose we were given this as a problem, right? The way you want to think about it is, okay, we're going to make this bottom thing, right? We're going to make this bottom part close to the absolute value of S squared, quantity squared, right? How small do we want this thing to be, right? If somebody says, I want you to make this thing smaller than epsilon, right? So they give you an epsilon. They want you to make this thing smaller than epsilon, right? This is what you want. Right? Well, if my bottom actually is S squared, right, I want this thing to be smaller than epsilon. So I want the top, what do I want the top to satisfy? Well, the top, I'd be better to be smaller than epsilon times S squared. Right? That's basically what you're gonna do. Okay? So, right, if we can make the bottom close to S squared and we make the top, smaller than this thing, then we're basically done. Okay? Okay, so you think, okay, so given an epsilon, choose n1 such that if we're past n1, then the distance of Sn from S is smaller than a half absolute value of S squared times epsilon. You'll see where this half turns up. Why did I put in this half? You'll see in a second. Okay. Choose n2 such that if we're past n2, then Sn is bigger than 1/2 the size of S. The size of Sn is going to be bigger than 1/2 the size of S. Okay, but you know that the size of Sn is going to become the size of S. So we can choose. We know that past some time, it's definitely going to exceed half of it, right? Right? Can do since Sn actually becomes S. Right? Okay. Okay. So then, right? Then if n exceeds the max of those two guys, we have that the absolute value of 1 over Sn minus the absolute value of 1 over S equals this S minus Sn over SNS. Right? So that is the top, you see, is less than 1/2 absolute value of S squared epsilon, right? And the bottom is bigger than 1/2 absolute value of S. So if I divide, it'll be less than that, right? Less than the reciprocal of that. So I get less than the reciprocal thing, like that. And that gives me the epsilon. Right? Let me spell that slightly more clearly. Right? We know that Sn is going to be bigger than 1/2 absolute value of S squared. And so that tells me that 1 over Sn is less than 1 over 1/2 S squared, absolute value of S squared. Right? So that's where I get this thing on the bottom here. Okay, and that's it. Okay, any questions about that? Let me spell this part out a little bit more clearly, just to be instructive. So look, this thing I can write as S plus Sn minus S, right? And by the reverse triangle inequality, I can write that as greater than or equal to S minus Sn minus S. So this is the reverse, remember the reverse triangle inequality that we saw before. Okay. So as long as, right, so choose n past which this Sn minus S is smaller than 1/2 of the absolute value of S, right? Then this thing is going to be bigger than 1/2 the absolute value of S. Okay, that's how we get that. So what I'm doing over there is explaining this kind of hand waving statement. You can do it. Here's how you would do it. Okay. Okay. So step back and think for a minute. Right? Like how did this work out? We were trying to show that this limit was 0. Trying to show that this limit was 0, right? What we did was we rearranged it, which was helpful because it got this term in, and this is the term we have control over, right? And then we think in the kind of what my PhD advisor would call morally speaking, he says, well, morally speaking, this thing on the bottom is s squared, right? Morally speaking, this thing on the bottom is s squared, and so we want the top to be smaller than smaller than epsilon times s squared, right? Right? So that's basically what you want to do, and then the rest is just figuring out, figuring out some numbers to make these halves work. Okay, but once you get to this point where you think, okay, well look, this thing is basically s squared, so all I need to do is make this thing smaller than epsilon times s squared. That's it. Okay, that's how you want to think about this sort of problem. Like basically this is this, so all we need to do is that. Yeah. Morally speaking was sort of the catchphrase of my advisor in graduate school, where everybody sort of parodied him for saying that. But not that he was somebody who was worthy of parody. He was a great mathematician. He was and is a great mathematician. Okay, let's go on. So we're going to do. Okay, so the next thing in the book is a statement about sequences in Euclidean spaces. I'm just going to let you read that. It's basically saying that, so you sort of sequences in arcane. So it's basically saying that if you have a sequence of vectors in arcane, okay, and you have some vector in arcane, then, roughly speaking, xn converges to x if and only if all the components, if it converges component-wise. Okay, so one has component-wise convergence. So I'll let you read that as an exercise. Okay. So either do it as an exercise or read it. Okay. And then there's some statement about like this vectors and limits. So like if you have sums of vectors, then the limit of the sums is the sum of the limits. If you have a dot product, the limit of the dot products is the dot product of the limits. This sort of thing. Okay. So it's not particularly interesting. I think it's more valuable to give to talk about some examples. So I'm going to erase this, and we're going to do more examples of limits. I don't know if you like this. Maybe you don't like this. So we're going to do whether you like it or not. We're going to do more examples of proving limits. Analysts think this sort of stuff is fun and interesting, but we also realize that there are other people who don't. Yeah, like Pfefferman, my advisor, said when I chose him as an advisor, I think he said that he praised my taste in mathematics. But on the other hand, there are people who, I had a friend in graduate school who said that her advisor said, analysts, they're just like the cockroaches of the mathematical world. And, like not even a nuclear war will just will rid us of them. She was a topologist. Okay. So let me put up a couple of things. One is an exercise that so this is an exercise, the so-called Squeeze Theorem. So I'm going to let you prove that from the definition. It's no harder than the things that we proved earlier. Okay. So it goes basically like this, right? If you have, I'm gonna write it in a kind of simple form that we're gonna use now. Okay, so if you have some sequences, so you have some sequences x of n, s of n. Okay, and if they satisfy this relation, right? So the x sub n's are always smaller than the s sub n's, and they're all positive. Okay. So say you know this. If s of n converges to 0, then you know that the guy in the middle also converges to 0. Okay. That's pretty straightforward, right? You know that you've got these sequences. The s sub n's are always bigger than the x sub n's, right? If the s sub n's converge to 0, then the x sub n's also will be forced to go to 0. Right, so you can almost see from the picture how your proof is going to go, right? You're going to be given an epsilon, and you need a time past which all the x sub n's are within epsilon of 0, but you know that the s sub n's are going to be there, so that's the end. Okay, so that's one thing that we're going to need. The other thing we're going to need is the binomial theorem. So let me just say it. Again, I'm not going to give the whole thing, but just the version that we need. So, so the binomial theorem for us is going to be like this, that if you have 1 plus x to the n, it can be expressed as summation from k equals 0 to n of n choose k, x to the k. Okay, where n choose k is n factorial over k factorial n minus k factorial. Okay, so binomial theorem. Okay, so we're going to need that. Okay, so those are things we're going to need. So I'm going to prove some limits of some common sequences. Okay, so the first one is the following, that the limit of 1 over n to the p as n goes to infinity is 0 for all p greater than 0. Okay. Okay, so think about what you need to do. So, always when you're doing a proof, you want to think, what are we being asked to show? So we want to show that, right, given any epsilon, there exists an n such that if n is bigger than that n, then 1 over n to the p in absolute value is smaller than epsilon. Okay, so generally when you're doing this sort of thing, you do some scratch work. You think, okay, well, let's see, right? I know, so you do some scratch work. Right, you think, okay, well, let's see. If n is bigger than n, then I know that 1 over n is smaller than 1 over a capital N. Right? And 1 over little n to the p is smaller than 1 over capital N to the p, since 1 over x to the p is an increasing function. Right? So you think, okay, so if 1 over n to the p is smaller than epsilon, then that'll do it for us. Right? We're trying to make this thing smaller than epsilon, right? But this thing is smaller than that thing. If we can make that thing smaller than epsilon, then we're good. Right? So in other words, i.e., we just need 1 over epsilon to be less than n to the p. In other words, n to be bigger than 1 over the pth root of 1 over epsilon. Okay. Okay. So you finish up your scratch work and you say, okay, let's write it down now. So over here you say, okay, we're given an epsilon, we want to find the n that works. We already figured it out over there. So let n choose any n bigger than 1 over epsilon to the 1 over p. Right? Well, 1 over little n to the p is smaller than 1 over capital N to the p. Right? But this, if this is bigger than that, then 1 over it is smaller than 1 over that. Right? So this is smaller than 1 over epsilon to the 1 over p quantity to the p. Right? And you see that that's epsilon. Okay, make sense? Okay, so this was maybe the simplest example, or a fairly simple example. It just relied on this fact, right? If n is bigger than n, then 1 over n is smaller than 1 over capital N. Right. That was kind of the key fact, and then, that's all we needed for this particular problem. Okay. Let me show you a more complicated, sort of increasingly complicated versions of this. Okay. So I'm going to erase this. Okay. Okay. So second one is the limit of p to the 1 over n as n goes to infinity is 1. Okay, so for all p bigger than 0. Okay. So this is something that you probably did when you were a kid and you got your first calculator, that you took any number and you started taking square roots of it, and you always ended up with something close to 1. Right? If you kept on taking repeated square roots, right, the more roots you took, the closer you got to 1. Even if you started with some tiny number like 0.0001, it would actually increase to 1, to your surprise. I don't know. Maybe maybe you didn't do that as a child. No? What? Okay. Okay. You must have had, I don't know what kind of childhood you had. But not, okay. Okay. We're going to prove it for p bigger than 1. Once you get it for p bigger than 1, you can actually just take reciprocals and then get the answer for p is less than 1. Okay. So let's just leave that out for a second. Okay. So let's just say, let's look at the case of p bigger than 1 only. So, okay. So we want to show that the limit of this thing is equal to 1. That's the same thing. We're going to rewrite it a little bit. Same thing as showing that the limit of this thing is 0, right? As n goes to infinity. Right? Okay. Let me call this difference x sub n. Okay, so we want to show that the limit of the x sub n is 0. In other words, we want to get some sort of control on the size of x sub n. Right? So our hope to control the size of xn, right? Right, and notice that these xabens are all positive numbers, right? Because p is bigger than 1, you're taking some root of it, and you're subtracting 1. Okay, so it's going to be, these are all positive numbers. Okay. Okay, so you say, okay, well, how am I going to get control on the size of this? Well, you say, well, look, observe, xaben plus 1 is p. Sorry, that's not p to the 1 over n. So x of n plus 1 to the n is p. Right? You think, does that give me any sort of control on the size of x of n? Well, if you think about the binomial theorem, this thing to the nth power has, as its first two parts of the expansion, it's going to be 1 plus n x of n. Right, this is the beginning of the binomial expansion of this product here. Right? This is the beginning. Right? If you take 1 plus x to the third power, right, you're going to get 1 plus 3x plus et cetera, right? So this is the beginning of the binomial expansion, and you see that this is good. This is good because you see that we're going to get some sort of control on the size. This thing is less than that, right? So we get that and xn is p minus 1. So xn is less than or equal to p minus 1 over n. Right? This thing is less than or equal to p. Right? Subtract 1 from both sides, divide by n. Okay? And we know that this thing is bigger than 0. And we see that this thing goes to 0 as n goes to infinity. So by the squeeze theorem, this thing goes to 0 also. Okay? So that does it for us. And I leave it as an exercise for you to show the case p less than 1 and bigger than 0. Okay. Just take reciprocals. Okay. Any questions about that? Okay. Let me show you another example. So the limit of n to the 1 over n as n goes to infinity is 1. Okay. This one I think would have been trickier to do as a child, right? Because you're not going to take 1,000 to the 1,000th root, 1,000,000 to the 1,000,000th root. That seems kind of less. I don't know. Maybe you do it if you're a Gauss or something. Okay. Anyway. So we want to show that the limit of n to the nth root of n as n goes to infinity is 1. Okay, so again we're going to play a similar game. So we let again xn. So again we rewrite this thing as we want to show that this difference is 0 as n goes to infinity. So we're going to play exactly the same game, but we'll have to vary it a little bit. Okay, so we let xn be that difference, right? And we see, of course, similarly, that 1 plus x over n to the n equals n. Okay. Now, suppose we play the same game as before, right? Suppose we play the same game as before. What's the problem? If we just use the first two terms of the binomial expansion, well, we're going to get xn is less than or equal to n minus 1 over n. Right? As n goes to infinity, this goes to 1. Right? Our xn is not trapped. Right? Xn doesn't. We're hoping that xn goes to 0. Right? That doesn't happen. Okay. So instead of using the first two terms of the binomial expansion, we use the second term. So n minus 1 over 2, xn squared. Okay, so we use the quadratic term from the binomial expansion. Okay, that's fair, right? Right? This thing is an entire expansion. We're just going to pick out part of it. Okay, that's going to be, in fact, strictly less than this. Okay, and so you work it out, and you get that xn will be less than 2, the root of 2 over n minus 1. N goes to infinity, and we get 0 again. Okay. Okay, let me do one more example. So this is number 4 in the text. The limit of n to the alpha over 1 plus p to the n as n goes to infinity for p greater than 0 and alpha a real number. Okay. Okay. So this again we're gonna control using the binomial theorem in the following way. So this one's a little bit trickier. So let k be this thing plus 1. This I don't know if you've seen this notation, but this is the integer, the greatest integer less than alpha. Right. Greatest integer less than alpha. Okay. So it's this kind of funny bracket thing. Let k be the greatest integer less than alpha plus 1, and then observe that then for n bigger than twice that sum, you notice that n to the alpha over 1 plus p to the n is less than n to the alpha over n choose k times p to the k. Okay, so we're trying to make this thing go to 0, and what we do is we use the binomial expansion on the denominator, right? And this is just the kth term. This is the kth term in the binomial expansion, right? Last time over here we used the quadratic term. Previously we used the first two terms. This is the p to the k term in the binomial expansion, right? So this thing is bigger than that. So when you divide by this, it's smaller than dividing by that. Okay. Okay. So then working this out, this is going to be n to the alpha times k factorial over n minus 1 n minus k plus 1 p to the k. This is just writing out what n choose k means. Okay, so just you dividing by this thing here is 1 over n choose k. Okay. And you notice that here on the bottom there are k terms, and each is bigger than n over 2. Right? Because n was bigger than 2k. Okay. So each of these terms is bigger than n over 2. Okay. So what do you get? You get that this is less than 2 to the k factorial over p to the k times n to the alpha minus k. Now, alpha minus k is less than 0. Right? Alpha minus k is less than 0. So you're taking so this is this is 1 over n, and this is 1 over n to some positive power, right? So that goes to 0. So this thing goes to 0 by the first limit that we got. Okay. Okay. So I think what you want to get out of this is that analysis is about controlling things, right? You try to take something and you break it into things that you want to control, right? And you use, in this case we've used the binomial theorem. It's sort of like an illustration of how to use the binomial theorem to get control over these things. Okay, but this is a general kind of thing that people do. Okay, that's it for today. Have a nice break, everyone.